Okay, good day, grade 11. I trust that you are well. Today we are going to look at a topic that may not actually seem popular in the grade 11 syllabus because one textbook states that this topic is self-study for learners, but I'm going to go through it with you nevertheless because it's quite an important topic because it helps us understand the nature of roots, and it also helps us to understand the function of a parabola, the quadratic function. So today we're going to look at the nature of the roots, right, of equations from a graphical perspective, from a graphical perspective. So I know what you're thinking. You're probably wondering, why can I not do this from an algebraic perspective? Well, you could, but of course, when it comes to algebra, we like to visualize what we are doing. So when we looked at the nature of roots, especially when we looked at the topic of nature of roots, we looked at the quadratic formula, which is x is equal to negative b plus minus the square root of b squared minus 4ac all over a. So what is the quadratic formula? The quadratic formula basically takes the standard form of a quadratic function. For example, let's say the standard form of a quadratic function we know is ax squared plus bx plus c, and of course if it's equal to 0, and if we want to solve for x, of course we can factorize this trinomial if it is of course a quadratic trinomial, but sometimes this does not actually give us two good roots. So what we can do is we can use this quadratic formula and we can find the values of x. But of course what we notice is that when we actually try to find the value of x, sometimes our roots, and when I talk about roots, I'm talking about the x value, the solution of this quadratic trinomial, or of this trinomial, sometimes your calculator will say that it's non-defined, or not non-defined, but non-real, right? Not undefined, but non-real. Undefined is, of course, the denominator of a fraction is 0, but why does it say non-real? Your calculator would just simply say mathematical error, right? Or maths error. It's because what's underneath the square root, what's underneath the surd, is a negative value. So when we looked at the nature of roots, we looked at what's underneath, let me actually get that right, what's inside the surd, which is b squared minus 4ac. And that is what we call the discriminant. That's what we call delta. So early on this year, we looked at delta, which is just basically what was inside the square root, which is b squared minus 4ac, right? So we said that if delta is equal to 0, so I'm going to start this lesson with just a quick recap. So that means when I substitute the coefficient of x in the place of b, if I substitute the coefficient of x squared, which is a, here of course we substitute using brackets, and of course the constant, which is c, in this place here. And if that delta value is 0, what does that mean? It means that this graph only has one root. And how we explain that, we say that of course the root are equal, sorry, are real first. That means it gives me a real value. That means if I have to draw the parabola is touching the x-axis, and because the discriminant is equal to 0, we say that the roots are equal, right? And of course, what's this, is 0 a perfect square? Actually it is. It's an integer multiplied by an integer. 0 times 0, 0 is an integer um, as well. So it's an integer multiplied by an integer, and therefore we can also conclude that it is also rational. That means the roots are rational. But what does that mean? It means that if I have a quadratic function. So let's say I have the Cartesian plane. And let's say, for example, I draw a parabola on this Cartesian plane as such. Let's call this parabola f, right? This quadratic function of f. What do you notice? You notice that this quadratic function is only touching the x-axis at one distinct point. That means this graph is decreasing, decreasing, decreasing. It hits the turning point and then it starts to increase thereafter as you increase the values of x. But it's not touching the graph at 2 points, right? Yes, it is touching the x-axis, but it's only, sorry, not the graph, it is touching the x-axis at 1 point. And because of that 1 point, it means that delta is equal to 0. That is what we mean by equal roots, right? Very, very important to get that. And let's say we calculate the discriminant from our quadratic formula, and it says that the discriminant is greater than 0, right? The discriminant is greater than 0. This basically means that, of course, the roots are real, right? And unequal, right? Will it be rational or irrational? That entirely depends on the value that you get for the discriminant. For example, if you calculate the discriminant and the discriminant gives you 16, right? Then I can say, yes, the roots are rational. Why? 16 is a perfect square. 4 times 4 is 16. Or if the discriminant is 25, then of course 5 times 5 is 25. So yes, it will be rational. But for example, if I say the discriminant is equal to 2, the square root of 2 is of course a non-perfect square, so then it will be an irrational root. So how will you interpret such a graph as this? It's basically, let's say we have our quadratic function. I'm going to be a bit quick on this recap because of course we looked at this when we dealt with algebra, but when I look at the examples, I'll of course go more slow on that. But it's very, very important that we first understand the nature of roots. And of course we're looking at a graphical perspective, so let's look at it on the graph. So let's say I draw a parabola. Okay, by the way, if you can recall from the previous term, we said let's call this graph G. As I was saying, as you can recall from the previous term, we said that we need a minimum of 3 points to draw a parabola. Usually the x-intercepts, right? The y-intercept and the turning point. And of course, some graphs do not have an x-intercept, which we will get to when the discriminant is non-real. That means the parabola is not touching the x-axis. Then you just need another random point that touches the graph as such. But in this case, you can see that we have our x-intercepts. We have a y-intercept, so we have our x-intercepts here. We have our y-intercept, and of course you need the turning point. And we discussed how to find the turning point. In such an equation, you could say x is equal to negative b over 2a, and you can find the x value of your turning point. Then you can substitute this x value into the function, and you can get the corresponding y value of the turning point. Or of course you can complete the square, right? That means you can take the standard form here, that is y is equal to ax squared plus bx plus c. You can complete the square and you'll have y is equal to a into x plus p all squared plus q, plus b all squared plus q. And of course we said that to find the turning point, we just put a c and a d on top of the p and q respectively. What does that mean? It means that the turning point of the parabola will be change to not change. So it will be negative p and positive q as such. So that is also a very important note. But going back to our point, you can see that the roots are real and irrational, and of course it depends on whether these values are rational or irrational roots, right? We know what a rational number is. A rational number is an integer divided by an integer. An irrational number, it's not the case, right? So a rational number is basically an integer divided by an integer. And some people always restrict the definition of a rational number. They tell me, okay, so it means that it is a fraction, right? It means that it's a number that can be expressed as fractions. So one could argue, what about pi? I can say that it's pi over 1. But no, pi is an irrational number because pi is not an integer, right? An integer, of course, we know what an integer is. It's all your whole numbers, 0, 1, 2, 3, 4, no fractions, no decimals in the sense of a part of a whole, and the negative versions of that. So negative 1, negative 2, negative 3, and so forth and so on. So although the denominator is an integer, the numerator, the top part of the fraction, is not an integer. So pi is an irrational number. Very, very interesting. But coming back to our last point on the nature of roots. So let's say, so what we can conclude is that, let me get this right, our roots will be real when delta is greater than or equal to 0 in these two scenarios, right? So when delta is greater than or equal to 0, then you will have a real root. But if it's just equal to 0, then of course you have an equal root. Or if it's just greater than 0, like for example, if delta is 16, then of course delta is greater than 0, the roots are unequal, meaning that when you talk about unequal, and this is where learners, or of course some learners, get a bit confused, but let me just clarify that here. When we talk about equal roots, we mean that there's only one x-intercept. So there's just one x-intercept. That means the graph, the parabola, the quadratic function is touching the graph at one point. When we talk about unequal roots, when delta is greater than 0, that means there are two, because we're dealing with the parabola, so it won't intersect at more than 2 points. A cubic function, which you learn about in grade 12, that graph actually intersects at 3 points and so forth and so on. At 3 points, right? Quadrat, yeah, 3 points. But a parabola is just simply 2 x-intercepts at most. So that is what we mean by equal and unequal. And before we look at the example, it's very, very important to properly understand these basics, right? And the last scenario is when the discriminant, when delta is less than 0. When delta is less than 0, that basically means the roots are non-real. Right? What does that mean? It means that the parabola will never touch the x-axis. The x-axis is basically your roots. Where the graph intersects with the x-axis is your roots. It's the solution of the parabola. Because remember, whenever we solve a quadratic equation, what do? We let the quadratic, we rewrite it in standard form, and that is, you have a quadratic that is equal to 0. So when the roots are non-equal, that means when the discriminant is a negative value, let me get that right, when the discriminant is a negative value, this is how the graph will look. And remember, this is in all my examples so far, I was just looking at the parabola being concave up, right, meaning that there's a positive a value. But of course, sometimes you can have a frowning graph, and that is when a is negative. So this is a nice smiling graph. But what do you notice? The turning point is somewhere here in this example. What do you notice is that the graph is not intersecting with the x-axis. That means if I have to find the x-intercept of this graph, it's not, I cannot find it, right? And it's just an important note before we look at our main example for today, right? When we look at the standard form of a quadratic, for example, y is equal to ax squared plus bx plus c, right? That's the standard form of a parabola, right? What do you notice about this c value? And this c value is going to play a very, very important role in the exercises that we're about to do. And if we understand what this x value does, it's very important. For the parabola will always have a y-intercept, right? That's something that it will always have. Like for example, this parabola that we looked at, it had a y-intercept. This graph has a y-intercept. The first graph we looked at had a y-intercept, which was here. The parabola always has a y-intercept. The problem comes with the roots, the x-intercepts. That's what the roots are, the x-intercepts of the parabola, right? So sometimes it may not have an x-intercept, but it will always have a y-intercept. So how do you find the y-intercept? We looked at this in grade 8, we looked at this in grade 9, and so forth and so on, To find the x-intercept, you let y equals to 0, right? But to find the y-intercept, you let x equal to 0. So of course, I don't have enough numbers here to find the x-intercept because we're using variables of a, b, and c, but I can find, let's look at what happens when I try to find the y-intercept, because the graph will definitely have a y-intercept. So I'm going to let x equal to 0. So we have a y is equal to a into 0 squared plus b into 0 squared. Sorry, b into 0 is b times 0 plus c. And of course, whatever the value of a is, I do not know what that variable a is. A times 0 is 0, b times 0 is 0, y is equal to c. So what does that mean? That means the coordinate of the y-intercept is basically 0, c. So c is basically the y-intercept. Very, very important. And intercept, I already wrote intercept. It's the y-intercept, right? And let's look at our first example for today. Now this is the fun part, right? Let's see what we can look at. And this topic, it's not very difficult, but it involves a lot of understanding. So please, before I look at example 1, make sure you understand the nature of roots. Make sure you have a good visualization. If the discriminant is equal to 0, understand what does that look like from a graphical perspective. If the discriminant is greater than 0, what will that look like from a graphical perspective? When I say that we have two roots, what does that mean? It means that the discriminant has to be greater than 0. That means the graph, the parabola is touching the graph at, or the x-intercept at 2 points, and so forth and so on, right? So let's look at this slowly. I'm going to try to go through this as slowly as I can because it can get a bit confusing if you do not have the basic foundational knowledge. And of course, the last thing that you needed to know was that the c value is the y-intercept. Okay, so let's get into it, right? Let's look at example 1. Let's consider a graph. Let's consider the graph of f of x is equal to, actually f of x is too famous. Let's make it g of x, right? Just fun. G of x is equal to, let me get a good example going for you here. It's g of x is equal to x squared minus 2x minus 8, right? And of course, if we complete the square, right, that's basically equal to x minus 1 all squared minus 9. Now you're probably wondering, okay, how did I get from this step to this step? It's basically the same graph, right? It's just rewritten in the other standard form, which is y is equal to a into x plus p all squared plus q. And again, if you're confused, let me just quickly show you how that was done. So we just basically took our g of x graph, first ensured, which many learners forget to do, we've ensured that the coefficient of x squared is 1, and in this case it is 1. Let's say, for example, the coefficient of x squared was 2. What will I do? I'll factor out 2 from this trinomial, right? In this case it's 1, so it's fine. So what I'll do is I'll say x squared minus 2x plus something squared minus something squared. It's called completing the square, and of course we drop down the negative 8. So what goes into this brackets? I'm going to take negative 2 and I'm going to divide it by 2. Yes, I'm going to divide it by 2, so that will give me negative 1, negative 1. Some learners write positive 1. Trust me, it doesn't really matter. Why? Because anything squared is a positive. So negative 1 all squared is positive 1. 1 all squared is also positive 1. So let's not just get too technical on that. But to factorize this, the reason why I like to keep the negative is because I'll just say x, and because it's negative 1 here I'll just drop down the negative 1 all squared. And here I have negative, this will become positive 1. Negative 1 minus 8, and that's negative 9. And that's how we get to this formula. And the beauty of this formula, and why I personally like this formula, is because it helps me find the turning point. We said the turning point is CD. Change, do not change. So the turning point is change, which is 1, do not change, which is negative 9. Because remember, we have to find, we have to look at the graphical perspective. So we need to draw this parabola. It's very important that we draw the parabola that we were given. And again, we need a minimum of 3 points. I already have 1 point, but to find the other points, let's find the x and y intercepts. And in case you've forgotten, we said to find the x-intercept, you let y equals to 0. So we have, remember, g of x is just a fancy way of saying it's all the y values where the graph, the y values of this graph g of x. So we have x squared minus 2x minus 8 is equal to 0. And of course, we looked at this in grade 9 and in grade 10. How will I find the value of x? I can use the quadratic equation, or I can just use the window method and factorize this quadratic trinomial. So it's going to be x squared minus 8 negative 2x. So I have x times x gives me x squared, and let's think about this carefully. Let's try negative 4 and positive 2. Why? Because negative 4 times positive 2 gives me negative 8. And when I cross multiply, so negative 4 times x gives me negative 4x, and 2 times x gives me 2x, and the sum of the products when I cross multiply, it's negative 4x plus 2x, which will give me negative 2x. So what are my two factors? It's going to be x minus 4 and x plus 2 is equal to 0. So I have x is equal to 4, or x is equal to negative 2. So yeah, what do I have? That, yeah. And of course, what does that mean? The coordinates are and 0, and we have negative 2 and 0. Okay, good stuff right there. Now we need to define our x-intercepts, sorry, our y-intercept. So we have our y-intercept, we're going to let x equal to 0, right? So g of 0 is equal to 0 squared minus 2 into 0 minus 8. That's going to give me negative 8. So the coordinate of the x of the y-intercept would be 0, negative 8. Okay, so now we have 4 coordinates. So remember, I told you you just need a minimum of 3 coordinates to draw the parabola. So we have more than enough information. So let's do that, right? Let's do that. Right, okay. To draw the parabola is going to be a bit tricky, but see what we can do, right? I am going to draw a quick sketch of the parabola. Of course, it's not going to be too accurate. And I want to draw it instead of using Sketchpad or GeoGebra, so that you can see that it's quite important just to draw a sketch of the graph. It's quite nice, right? So let's quickly do that, right? So let's first start off with our x-intercepts. Our x-intercepts were negative 2, positive 4. Right, good stuff. Now let's start off with, then we had our y-intercept, which was 0, negative 8. So 0, of course, is at the origin here. Negative 8, let's make it somewhere at the bottom here. That's quite a large number. And we have negative 9 here as well. So that is, this coordinate here is our y-intercept. And of course, our turning point, which we said was, we did calculate the turning point, right? We did say it was, we did say that the turning point was 1 and negative 9. So let's say 1 is somewhere here. And I'm just drawing a very quick sketch for you, and I'm sure if you have the time you can take your pencil and ruler and make it much more neater than me. Right, now the tricky part, of course, it should be more accurate in your book, but now we just join all our dots together. And remember, the parabola is a free line graph. That's not the neatest parabola, but it's okay. Right, so this is my parabola G, right? Now what we're going to do is, we are going to look at question 1. So we haven't looked at the questions yet, right? So question 1. And I'm going to write out question 1 for you, right? It says determine graphically the values of k. Okay, actually, let me actually write that down, right? Determine, so you can see the question that I'm looking at. Determine graphically the value of k for which, right? And the first scenario is when x squared minus 2x plus 8 is equal to 0, right? Has equal solutions. So what do they talk about? What do they mean when they talk about solutions? They are talking about the roots, right? They are talking about the roots. Okay. Equal solutions. Okay. Which basically means the roots. Okay. So before I go on to B, let's quickly tackle A. What does K stand for? I hope you all know this. I don't like how this K is looking. It should be K, not look like an X. Right. So when we talk about K, we are talking about the y-intercept. Right? So when you look at this graph, right, remember, in case you have forgotten, this was the equation of the graph. G of x is equal to x squared minus 2x minus 8. If you look at this graph, you can already see that the y-intercept is negative 8. Right? But you can, how will I interpret the roots of the graph without doing the algebra? Of course, if you want to do the algebra, you can. You can say delta is equal to b squared minus 4ac. My b value is negative 2, so it will be negative 2 all squared minus 4 into the coefficient of x squared is 1, so that's 1 into negative 8. And that will give me 4. What is that? That will be a 4 times 8, and that will give me 32. So it will be plus 32, which will give me 36. Right? So I can see that, of course, my roots are real, they are unequal, and of course they are rational, because 36 is the perfect square. 6 times 6 is 36. So what we can, and you can see that that is true as here as well. This number, negative 2, is a rational number, and 4 is a rational number, therefore the roots are rational, as you can see. But these roots are unequal. That's the key word. What is my question asking me? How can I change this equation? Right, so that instead of having a negative 8 here, this y-intercept is of course going to change. It's going to shift either up or down, such that the graph has equal roots. Right, the exact same graph, except now the graph is being shifted up or down. So how will this graph look? So remember, we said that the turning point is 1, negative 9. That's the turning point. But if the graph has equal roots, that means the turning point is going to touch this graph at one point. So my new graph is going to look something like such. Right? And this is going to be my new turning point. It's going to be 1 and 0. Right? Now this looks like a graph that has equal roots. Why? Because we said equal roots is when the graph touches the x-axis at one point. And in this case, it is touching the graph at one point. Right? But what do you notice about the y value? It changes, right? It changes. So what we did was, let's look at the turning point. The turning point originally was 1 and negative 9. What did we do? We shifted the graph 9 units. Yikes, let me get that right. We shifted the graph 9 units up, right? So that's what we did. We took the original mother graph. We took this original mother graph, x squared minus 2x minus 8. And what did we do? We shifted it 9 units up. Now what's the equation of the new graph? The new graph would be y is equal to x squared minus 2x negative 8 plus 9 plus 1. So what is my k value? My k value is 1. So k actually represents the y-intercept. So this coordinate here is 1, which makes sense because negative 8, you have to add 9 units to it, it's going to give you positive 1. So k is equal to 1. K is equal to 1. Right? And again, we solve this graphically. Okay. Now let's move on to question number 2. Right? So you can of course press pause on this video and take down the notes, but I'm just going to erase each one and do the new scenario as we go along. Right? So let's look at scenario number 2, or question number 2 rather. Question B reads, okay, determine graphically the values of k for which x squared minus 2x plus k is equal to 0 has non-equal roots. Why do I even say equal? Non-real roots, rather, or non-real solutions. Okay. So now we have a visual of how the graph looks. Let me get it right. What can I use? And let me just erase this here. Right. So we have a visual of how the graph will look, right, if it has an equal roots. Right. So let's keep that in the back of our mind as well. Okay. Now let's see what will happen if the graph has non-equal roots. How will the graph look? Right. Firstly, the x value of the turning point will still be 1, but the graph will not intersect with the x axis. There will be no x-intercept. Right? So that means if I have to solve for this new graph, whatever this k value is, and if I have to find the x-intercept, I will not be able to find it, right? Because the graph will not have x-intercepts. My graph will look something this, right? Just a visual, right? The graph will look something like this. So let's just use the previous equation that we had. Let's use this rate graph. What was the equation of the rate graph, if you can remember? The equation of the rate graph, I believe, was y is equal to, we said x squared minus 2x plus 1, and k is equal to 1, right? So if, let's get this right, if k is 1, if the y-intercept is 1, notice that the graph has one turning point. That means the graph is intersecting with the x-axis. But what if k is 1.1? That means it's here, right? Let's say it's somewhere here, or let's say k is 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 any value that's greater than 1. This graph will never intersect with the x-axis. That means if we shift this graph 0.1 units up, then this turning point will also be shifted 1 unit up. That means it will be 1 and 0.1, because this graph is shifting up the original graph. So when k is greater than 1, then the graph will have non-real roots. This graph will not intersect with the x-axis. Let's look at the last, the penultimate question, the second last question. If we have determine graphically the values of k for which x squared minus 2x plus k has 2 real and unequal roots. Right? Okay, this is quite interesting. Okay, so let's look into it. Let me use green. When will it have 2 unequal roots? When the graph already g of x meets that definition. But of course, there could be many values of k that could meet that definition there as well. Like for example, if I draw a graph like this, if I shift the mother graph 1 unit down, of course, if I shift the mother graph 1 unit down, it still has 2 real and unequal roots. If I shift it a few units up, I'm not sure by how many, but if I shift it by a few units up, it still has 2 equal roots. So if I look at the read graph. The read graph is quite important. Why? Because that's where we have where the graph has equal roots. If I shift this graph, I know there's a lot of graphs everywhere, but that's why graphically it can be a bit messy. But I like to have good visual. I hope the colors are helping you here. So if I look at this read graph, right? Remember we said that the k value was 1. If I shift this graph down, like for example, if the y-intercept is now 0, then the graph will have two x-intercepts. Or if I shift it 0.1 unit down, right, then of course, what will this be? This will be 0.9, right? But still the graph, because I shifted it down, the turning point will shift down and the graph will still have two real and unequal roots. So what I'm trying to say is that this will be the case when k is less than 1, right? And let's look at the last and final question. Okay, I do not like that this graph is very messy at the moment, but is there something I can do about that? Let's see if I can perhaps erase all of this for now so that it does not confuse you too much. Right, okay. So I hope that this is starting to make sense. And again, it might seem a bit confusing at first, but if you have a strong foundation knowledge of the nature of roots, as I explained in the beginning of the video, then it will all click together. Trust me, it will make much more sense. Okay. Let's do that. Let's erase this as well, right? So let's just keep this red graph, and let's keep this our solid graph, which is the original graph geometric, right? The graph that we are referring to. Okay. Okay, good stuff. Right. Okay, we are back. Let's quickly look at what we need to look at. Okay, I'm sure I can make this pen a bit thinner. Right, let's look at question D. Even thinner there. Okay, let's look at question D. Question D is when we have x squared minus 2x plus k is equal to 0 has two real positive roots. Now they start to get a bit trickier, because when we looked at two roots, we said, okay, when k is less than 0, that's perfectly fine. Right? But what happens now when we only want positive roots? Because when k is less than 0, sometimes the graph could have one negative x value, one positive x value, meaning one negative x-intercept, one positive x-intercept. So in this situation, let's look at the graph when the k value is 0, right? So let k be 0. So let me use a different color here. So when k is 0, when k is equal to 0, right? What is the equation of the graph? The graph is x squared minus 2x plus 0, right? So what does that mean? It means that the y-intercept is 0. So let's say this graph looks too similar to the yellow graph, so I need to find another color. Let's try purple, right? So let's say this is the graph that we have in question. Yeah, I'm not too sure what the x and y intercepts at the moment, but let's just say this is how the graph more or less would look. It may not be an exact sketch, but the graph will look more or less like this, right? So as you can see, we have two x values, and what is one of the x, what is the y-intercept? It's 0. So let's look at when we have positive roots is when, of course, any value, any k value that lies between 0 and 1, we will have positive x values, right? We include 1. Now that's something that's very debatable. Should we include 1 when we are considering this graph? Well, technically, the x value, the root, okay, let me get that right. Sorry, my pen just froze. Yeah, let me get that right. It's debatable because if I look at 1, right, what is the root? The x value is 1, and 1 is a positive, so it's not much of a debate. X is a positive root, so you have to include 1 as well. But when we look at when the k value is 0 for this purple graph, what is my x value? Right? What is the x value? Let me get this right. I'll have one x value that's positive, perfectly fine, but one x value is 0, and 0 is not a positive value. 0 is neither positive nor negative. So the k value, so the answer will be when k lies between 0 and 1. And when k is equal to 1, what is the root? The root is 1. And last time I checked, 1 is also positive. So we have to include 1 as well. Right. So that is what we looked at in this. I think we'll have to separate this lesson into two parts. In part 1, we looked at the effects of the y-intercept, or the turning points of the graph, when the nature of roots, the x-intercepts change. Right. So when the x-intercepts change. For part 2, we are going to look at the effect of the points of intersection of two intersecting graphs when the nature of the roots of the intersection changes equations. Oh, that is so fun. But let's have a good understanding of this first. So I do not want to make this video too long, or else it will take a bit too long to process when I'm uploading the video. So I'm going to separate it into two parts. So for part 1, we just looked at the effects of the y-intercepts, right? So let's have a good understanding of this lesson, and then we will look at part 2, and that will be very interesting as well. Okay, I hope this helps, and I hope that you are going to practice every single example that I did, right? I know a lot of textbooks have examples of this, and some textbooks do not, because it's a topic that's regarded as self-study. But again, I do not want you to self-study and be confused. I looked at this example with you as well, so please look at it as well and try to have a good understanding of it. Okay, thank you so much, grade 11s, for watching this video.